It's a real joy to be joining you all and being able to share my research again. So yeah, my perspective really is to try and learn about the climate system and the interactions between climate and ice sheets by looking at the past when we've had major changes in climate and sea level and ice sheets. So I'm going to talk about that perspective and give you examples of the work we do and we have done recently. And I've put down some names here. I might have forgotten some of the people that I've had the chance of working with that have done a lot of this work. And some are climatologists, some are glaciologists. I've also worked with people that model sea level. And I have recently had some really strong collaborations with statisticians that not only teach us in the group how to use good techniques to quantify uncertainties, but also develop the techniques themselves, because a lot of the time we need newer tools, bespoke tools in statistics to really address these challenges. So what I'm interested in is thinking about really the worst case in sea level rise. I think as a community, we've done a fantastic job in getting together to, with the climate modelling and the ice sheet modelling internationally to do inter-comparison projects and project future changes in the sea level, but there are still huge uncertainties in the worst case scenario. And this is important for communities living in coastal areas, but also for anyone that relies on infrastructure that is near the coast. And it gets really scary when we think about all the nuclear power plants that are near the coast. And for these cases, we need to think about even the low probability events, the things that might rely on very speculative events that we were hearing about last week, or even the worst case scenarios in terms of our emissions of CO2 and climate change. And we've got some tremendous developments in the ice sheet modelling side of things over the last couple of decades, and the pace of developments in the ice sheet models really picked up. We've got a huge variety in the models, and what we find is that the newer models, the very complex ones with all the bells and whistles, often actually very highly tuned to the model, because we have such great information from satellites and other remote sensing on, for example, the velocities of ice sheets. And I put here a figure showing, the velocity coming from an ice sheet model, but that is tuned to a satellite data set, and you can see those beautiful ice streams there. But to do this, in order for our models to be able to simulate those ice streams so well, we calibrate or invert some unknown parameters in 2 dimension. So we end up with some very intricate patterns in some of the inputs to those climate models that represent processes that happen either within the ice, in the ice streams, or at the base of the ice streams. Now, if we use these models to simulate the near future, maybe a couple of decades, it might not be so bad to think that the way those processes might operate similarly in the near future. But when we go further away from the modern day configurations, then we can lose confidence in that, especially if we're interested in the longer term future on multiple century timescales for planning of infrastructure, or the worst case scenario. Then can we believe the models that have been so highly tuned to modern? That I know that there are newer techniques that involve actually calibrating the models or initializing them over the historical period. Even then, we haven't seen so much changes in the ice sheets over the last couple of decades compared to what we are anticipating in the next few centuries. So I'm interested in looking at the past, and in the past there's been some really huge changes in the ice sheets. In particular, if we look at the Quaternion, we had the Ice Age period, essentially. We had ice covering the whole of Canada and large parts of Northern Europe. And this is a diagram showing you here at around the time of the last glacial maximum, what the ice sheets look like in the Northern Hemisphere. And we have a wealth of information on these ice sheets. This is just a couple of examples of reconstructions. We have very good knowledge of the extent of the ice sheets at their maximum in particular, but also as they retreat through the last deglaciation. So over the last 20,000 years, we have some good timing of these retreats, and the different lines here, you can see some figures represent margins at different times. So this is for North America, for example. This has been done. On the right, you can see a similar exercise being done for the Eurasian ice sheets. And in the middle, maybe a less well-known ice sheets, and in particular, a very small contribution in terms of sea level change, but very good detail in its reconstruction. I think it's probably to do with the number of people being able to visit the sites on our small island. So recently, we've had a big project finished called British Chrono that reconstructed the pace of retreat of British and Irish ice sheets in the marine sectors and on land. I'm going to show you some of the applications of this work. It's not just the extent of the ice sheets that we've got so well reconstructed. Where ice has disappeared, there's less evidence on the ground, on the landscape. That is telling us things about how the ice sheet was the flow of the ice sheets in the ice streams. In particular, this picture shows what we call megalineations seen in Canada. And it's very similar to actually what we see at the bottom of the Antarctic ice sheets using remote sensing techniques. So we have compilations of the position of the ice streams, those fast flowing corridors of ice, and also the direction of the ice streams. So this is telling us something interesting about a long timescale evolution of the ice sheets. But not only this, we have evidence from work that we've done that there has been instabilities in the ice sheets in the past that are relevant to the future, because the same mechanisms operate in the past and the future. I'm showing you here just to highlight some work that I've done showing what we call the saddle collapse instability, which involved the surface mass balance. When two parts of an ice sheet separate, it causes a big sea level rise. And this could also occur in Greenland in the next millennia. We've also identified that here's the British and Irish ice sheets during the last deglaciation. And in particular, part of the ice sheet called the Minch ice stream was subject to marine ice sheet instability. We were able to do this by combining evidence from British Chrono project with some numerical modeling from Gandhi et al. And this marine ice sheet instability is the #1 threat in terms of sea level rise for the future. And this is an example of the areas here, the probability of retreat in the marine sector of the Antarctic ice sheet in the future. And this is due to this marine ice sheet instability. So we have the potential, by looking at the ice sheets and modeling them, to constrain those key processes. So in this talk, I'm going to give you a couple more examples in more detail of what we've done by modeling these past ice sheets. One thing I want to talk about is how we use them to test and develop our ice sheet models, and also testing a couple climate ice sheet model at the last glacial maximum. And all of this, I'm going to show you how we use techniques to quantify uncertainties that are quite complex. So first, looking at testing ice sheet models and developing them. So for this work, we used the BISICLES ice sheet model. It's my favorite ice sheet model. It's efficient because it's got an ability to refine the grid, so the resolution where it's needed. In particular, at the grounding line, this is a transition between the grounded parts of the ice sheets and the floating parts of the ice sheets. And it's been shown that we need a quite fine resolution to be able to represent processes quite well there. And in particular, the marine ice sheet instability that I mentioned. So BISICLES is able to simulate this mechanism of ice sheet instability accurately and efficiently. Just to give you a bit more of a sense of how it fits within the sort of hierarchy of ice sheet models, this is a diagram that's quite useful, showing us the full range of ice sheet models we have. At the top is what we call the full Stokes model, if we consider all the balance of forces within the ice sheets. At the bottom, it's kind of an old style of ice sheet models, the one I started with through my PhD, a shallow ice approximation model, where we simplify very much these equations. So there's also a shallow shelf approximation, which can represent the floating parts of the ice sheets. Now, some models are hybrid. They can combine the shallow ice approximation with the shallow shelf approximation to simulate the whole of the Antarctic ice sheets, the grounded parts and the floating parts. But it becomes difficult to represent the transition between the two. And this is something that the higher order models are thought to do even better. So there are fewer assumptions in those kinds of models. There's no need for having a different approximations for the floating parts and the grounded parts. But it still also has some simplifications in the models to allow them to run fast enough to simulate centuries or millennia in the ice sheet model. So this is what BISICLES uses. And as I told you earlier, it's also got an adaptive mesh, which means that we can find a resolution where is needed in the ice streams and at the grounding line. It includes a range of different processes in there. Recently, there's been some development to include glacial ice static adjustment. It's got different ways of representing calving, which is quite in certain parts. Some different ways as well of representing ocean melt. And I'm going to talk about developments we've done to the sliding law. I should also say that it's coupled to their system models. So as I mentioned earlier, that some of the complex models like BISICLES, we rely on inverting parameters that control the sliding, but we can't do this for the paleo. So what we've done is actually develop the model to include a simple hydrology scheme, so the ability to have water pooling at the base of the ice sheet where it's warm. And we've included a new development in sliding law from Tsai et al. That combines sort of a power law, Vietman sliding, with a more Coulomb law, which is sort of plastic behavior of the ice sheet. So we end up having a different sliding in the slow moving parts in the interior of the ice sheets, and then it transitions to the Coulomb regime in the fast sliding part of the ice sheet. So I'm just giving you a broad overview here. But what it's been shown that is quite important. It changes the behavior of the ice sheets in how the grounding line retreats, for example. But what it's also been found to represent the deformation of till at the base of the ice sheet. And we applied this new development, BISICLES ice sheet model, to British and Irish ice sheets. Yes, there's an animation here. We simulated kind of the growing of the British and Irish ice sheet. And you can see here popping up in red are the ice streams. And in blue are the more slow-moving parts of the ice sheet in the interior. So here we haven't inverted or given any distribution to the sliding parameters. It's kind of uniform parameters. So the only thing generating these ice streams is these new processes that we've put in. So yeah, our ice streams are self-generating. They are deciding where the position is, but also you can see that there's quite some fluctuations in the velocities during the growth, and actually an acceleration of the ice streams during the deglaciation. So this was work done by Niall Gandy during his PhD, and he's found that the positions of the ice stream matches very well evidence of stream activities in the past. And he's even found that in some places where there wasn't evidence of an ice stream, when he was looking at the data, he could identify some evidence. So he's been able to document new ice streams. So this is a way in which we've used past ice sheets to improve our ability to simulate past and future ice sheets. I'm not showing here, we're now doing some work applying this scheme to the Greenland ice sheet at present day. And the first work is showing some very positive signs that the model does a good job at simulating modern day Greenland ice streams. But now I want to move on to talking to you about coupled climate ice sheets modeling. And this is particularly relevant when we look at in the future of Greenland ice sheets, where the surfaces, the surface mass balance processes, the melt and the accumulation are very critical for simulating the evolution of that ice sheet over the next century. And simulating this surface mass balance, so the balance of accumulation of snow and melt at the surface of an ice sheet is complex. And to do it well, we need to consider energy fluxes and also precipitation, accumulation, and processes that happen in the snow and within different layers of the snow. So it's best done within an energy balance calculations done within a climate model. But it also requires high resolution, and often climate models are run globally with not too many grid boxes covering Greenland, for example, whereas the areas in Greenland where melt occurs are quite narrow corridors, narrow regions around the ice sheets that are actually quite, where the topography is quite steep. So we need to have some ways of downscaling really our ability to simulate the surface mass balance. And here the model that we're using is called famous ice. So famous is quite a low resolution system model, but it's very fast. So we can run in more than 500 model years per day, which allows us to simulate very long timescales, particularly relevant for looking at the past. And it's coupled to two ice sheet models. One is Glimmer. It's a shallow ice approximation model, so one of the simpler ones, but very fast. And the other one is BISICLES that I presented earlier. So the model in the climate side is quite coarse, resolution of about 500 kilometers, so it's quite low resolution for the ice sheets. But it has a way to calculate the surface mass balance at different elevation through within a grid cell. So for each grid cell that has ice, we have levels, 10 levels for the surface of the ice. And for each of these levels, we calculate the surface mass balance. And this diagram here is showing you the surface mass balance of those 10 different elevations and how that varies for this particular grid cell. And then we use this information, so we've got surface mass balance calculated in 3 dimensions. We pass it on to the ice sheet model that then linearly interpolates to decide what is the surface mass balance on the higher resolution of the ice sheet model. So this has been documented and applied as well to simulate modern day Greenland, and does quite a good job at simulating the shape and the surface mass balance of Greenland today. This is compared to, for example, the regional climate model MAR. We don't have all the details, but you know, it does a reasonable job for the whole ice sheet. And then it's been applied to simulate the long-term future of the Greenland ice sheets and tests whether under some scenarios we can recover. So we've applied it to simulate the last glacial maximum. So that was about 20,000 years ago. There were lower greenhouse gases. The CO2 was 180 ppm, for example. Much cooler climate, and large ice sheets covering the Northern Hemisphere. And our first application of the model wasn't so successful, so we just took it out of the box as it was calibrated for modern Greenland. And this is showing you this pre-industrial Greenland, quite stable ice sheets. At the LGM, it's just collapsing. And this is through time. You can see that we're losing all the ice covering Canada here. So this is obviously wrong. So what we've done is a lot of work to detune this model. And what we were concerned about using famous is, oh, yes, there's a question.
Really quick, yeah, sorry about that. During the LGM, the ice sheet reconstructions for the Laurentide they vary the gamut. So what did you start with, and are there other possible Laurentides that you could have started with that would have been stable?
Yes, I'm gonna briefly talk on that later. So we ran lots of simulations, and I can address that specific question later on, if you don't mind. So here we started from an intermediate ice sheet, with the hope that we would grow the ice sheet to a full size. But we've since done lots more work varying the initial conditions, and that does matter quite a lot. So what we were really concerned with is that famous was simulating the climate well. So we decided to simulate the climate just with atmosphere only and fixing the ocean condition, the sea surface temperatures and the sea ice conditions in order to, let's say, it's a way of doing data assimilation on the climate side of things, and to control and remove some of the biases on the climate side of the couple model. So I'm just going to show you quickly how we did that, and there's some publications that are in review at the moment describing this. So we used data from around the world, reconstructing the sea surface temperatures at the last glacial maximum, and a range of model simulations from PMIP3 and PMIP4. These are model and comparison projects where a variety of models have been used to simulate this time period. And we merged the two together to really present, to have a best guess at what the sea surface temperatures could be. But also we learned the relationship between sea surface temperature and sea ice concentrations. So we were able to simulate or to reconstruct both. And I'm not going to go into the details here, but we have a method that allows us not to just have mean reconstruction, but actually generate an ensemble of plausible sea surface temperatures and sea ice concentrations that are compatible with each other, and that physically plausible based on the information from the climate models. We also varied a range of parameters, both in the climate models, for example, in the clouds, the way the surface mass balance was represented in the model, and also within the ice sheet model, for example, how the flow or the sliding is represented. So we used a protocol from the PMIP paleo model and comparison project, phase 4, for simulating the last glacial maximum. And we started here, as I said, from a mid-sized Laurentide ice sheet. So we did hundreds and thousands of simulations through multiple waves. I'm going to talk to you a bit about this. The first wave of simulation went like this. So we decided to stop and check our simulations at regular intervals to see how they were getting on. And the vast majority just deglaciated. So our simulations tended to really lose volume very quickly. And that's what you can see on the left side of things. And only a handful of simulations were able to grow from our mid-size ice sheets to a glacial maximum. So what we wanted really is to have more than just a handful of simulations that were reasonable. So we designed a way to run shorter simulations that we then linked to our best guess at what the equilibrium ice volume would be. And that's through a technique called emulation. So it's essentially a statistical model of how the equilibrium ice sheet volume is a function of the initial surface mass balance. And for this, we only really needed to run the model for 20 years. So we could run lots and lots of simulations, just very short period, to guess where the good parameter combinations would be that would give us a range of ice sheet behaviors that is compatible with the geological evidence. And you can see on the right here, the red line is the reconstructed ice sheet extent. And the colors show the percentage of simulation with ice cover. And this is a much better match. So some of the simulations still don't have enough ice in some areas. Some have a little bit too much in Alaska, which is a very common feature. But the main thing is that we have lots more simulations that are reasonable. And you can see here in black, these sort of the space of parameter. These are names of some of the parameters that have a big effect on the ice sheet's size and volume. And most of them control the albedo. And the red points are the simulations in the final wave that are reasonable. And you can see that we managed to cut part of the parameter space that we no longer think is reasonable. And in particular, that has really constrained the albedo of the surface of the ice sheets. It was previously very low due to some parameters controlling this. And we ended up with some best simulations having higher surface albedo. So this is all I'm going to say for you today. I've shown you that some mechanisms of ice sheet instability operate in the past and the future. The same mechanisms. We have gold mine of information of past ice sheet evolutions. And what we're doing here is developing some new techniques to quantify this uncertainty and applying some coupled climate ice sheet models, both to past periods, but also to the future. And the aim really is to go beyond the last glacial maximum, where we have quite stable ice sheets, and look at periods where the ice sheet was unstable, to see if those can provide further constraints on both our climate models and our ice sheet models. But we've already seen that the last glacial maximum is a good test for coupled climate ice sheet models, and that just tuning those just for modern day can cause some big problems for the sensitivity of the models in the past, but also in the future. So thank you.
Thank you, Lauren. That was a lovely talk. Do we have any? Please, if anyone has any questions, let us know. You can raise your hand virtually, or you can post your questions in the chat, and we will address them.
Maybe I can start by coming back to Allegra's question. I haven't said very much here about the initial conditions for the ice sheet. So here we started from a mid-sized ice sheet, which actually came from our some simulations of the deglaciation, to grow the ice sheet to a full size. More recently, we've tried some simulations with different initial conditions, and actually with the BISICLES ice sheet model. And we find that we're close to a point of instability, in essence, where some changing the initial condition a little bit can really change whether you're growing the ice to bigger ice sheets or shrinking the ice. But yeah, those are very recent results, so maybe you can share them in a couple of months' time.
Give people a moment. Do you have a sense of how what initial conditions, for example, are so crucial in determining the path of which the ice sheet will go down this by stability?
So at the moment, what seems to be important is the geometry of the ice sheet. And so in general, the thickness, but it could be that, you know, in particular, the shape of the ice sheets around the margins might be important. But it is because of the height mass balance feedback. So the higher you go in altitude, the less melt you have, the more accumulation. So you can end up with more area above the within the accumulation zone, and less area in the ablation zone. So the shape of the ice sheet can have quite some impact on the overall mass balance. At the moment, that's what we've tested. We're about to look into more detail about the effects of the dynamics of the ice sheet in the initial condition. So what we're trying to do now is spin up the temperature of the ice sheet and see how that affects the velocity and the dynamic behavior of the ice sheet.
All of a sudden, we're getting a few questions. So I think first is Gavin, and then Lawrence, and then Letty. So yeah, Gavin, please.
Hey, Lauren. Great to see you. A great talk. Thank you very much. If the albedo is the biggest issue, right, then the things that affect the albedo are obviously going to be very important. And so the things that people have thought about are obviously things like dust and soot deposition on the ice sheets. But of course, to get that, you need to have models of the LGM that contain dust and black carbon and deposition parameters. And so have we, is there some way that we could perhaps help out by using your ice sheets as inputs to models that have composition that allow for deposition fluxes that you can then use to change your albedo parameterizations? Is that a possible path forward?
That's a very interesting question, Gavin. Yeah. So what we found in Famous, we don't have such
right.
Dust is very simple, and what we find is that the clouds might not be behaving so well, so they're causing some biases in the model. So that's why we have such a strong impact on the surface albedo parameters. So what happened really is that when the model was tuned to modern day, there were the biases there was in the clouds was compensated by some lower values of albedo on the surface of the ice sheet. And when we take the model to simulate the last glacial maximum, a different ice sheet, so lower in latitude, for example, the clouds are different, so those biases don't compensate anymore. But I do think that is probably applicable for models that do simulate clouds better. So that's the first hurdle, I think, is our ability to simulate clouds at modern day and in various different time periods. And you've mentioned the dust in particular. That will have a big impact, I think, on the last glacial maximum. And there's some big challenges there in our ability to model deposition of dust, or to model how that, or even black carbon, affects the surface mass balance of ice sheets. But our framework is a way that we can use ice sheets as a way to test or even calibrate the full Earth system model, in a sense. So yes, we can do that eventually, but I think we'll have to tackle the challenge of the clouds before we can say something about dust. Does that make sense?
Is there surface mass balance simplified, or is it you actually do for full surface mass balance? Would it even matter?
Yeah, it is full surface mass balance, but it is not as complex as what's included in regional climate models like ROCMO and MAR, that maybe represents more layers of snow, and how the snow ages, and how the albedo of the snow might change with its age. So it's not as complex as those.
Do you have an input of particles into those albedo schemes? Where would that come from if you do?
Yeah, some regional climate models have tested sort of taking into account pollution, for example, black carbon, and its effect on surface mass balance. There's a little bit of work on that, but not very much. And certainly there'd be a lot of work to take into paleo context. But yeah, I mean, that would be amazing. I think probably the next steps are to apply more complex regional climate models to the paleo. But obviously Laurentide ice sheet is much bigger than Greenland ice sheet. So
is there a Laurentide Mar version in the works?
No, not yet.
I really don't think that that's a useful thing. I mean, but taking the physics that those models are using and implanting them within the global models, I think that's a much better path forward.
So the thing for the surface aerosol depositions that most ice sheet modelers always tell me is that, oh yeah, it makes it so dark, but then you get a fresh layer of snow and it doesn't take much before the aerosols are moot. So yeah. You can have an aerosol deposition, but layered under like a centimeter of snow deposition, it doesn't make a difference. That's critique that I always hear back.
Yeah,
I don't know if it's actually true. I've never been on the ice sheet myself to see.
But in the summertime, and this is low latitude, you have a lot of time when it's not going to be snowing at all. You can dismiss that out of hand.
Yeah, so I think there's definitely some ongoing work to try and understand these processes a bit better, and how to parameterize them in models. But as you can see, that already our constraint on modern surface albedos aren't that strong. But what we're finding is that we should be careful when calibrating our couple climate ice models to the modern, not just trying to do something that will compensate for biases.
And do you have refreezing process?
Yeah, refreezing happens within snow layer.
Cool.
Next up, we have Lawrence.
Yeah, this mostly you've been talking about atmospheric effects on the ice sheet, but I was wondering whether there was any sense of the sensitivity of those ice sheets to the ocean. What sort of control you have on what the oceanic forcing would be?
Yeah, and this is particularly very important for Antarctica, where it's number one reason for the retreat. It's a bit harder in the paleo to have information about the ocean conditions. And big source of uncertainty, even at modern day, is how the ocean conditions translate into melt under the ice shelves. And that is very much dependent on the shape of cavities under the ice shelves. So it's a very local thing, but also as the ice retreats, cavities grow, they change shape. So there's big effort internationally to develop better models to represent those processes, and actually coupled ocean ice sheet models that have high resolution under the ice shelves. So I'm expecting that we will make a lot of progress in how these processes can be parameterized for using on the paleo context, where there is no point applying high resolution in the paleo if we don't have a good handle on the ocean circulation.
So are your statements that various things like albedo are the most important, they're based on more on having information, more information about the atmospheric forcing variability than you do for the ocean, and that potentially what's happening around the perimeter with the ice shelves, and that would get into the calving flux laws and so on. Maybe that is also important, but you just don't have the ability to test it as well.
Yeah, that's not what we've been able to focus on so far. So for Greenland, the albedo is important, and for Antarctica, you really have to account for ocean processes. In terms of the past ice sheets, so the North American ice sheets very much land-based, and so it's responding to surface mass balance processes primarily. The Eurasian ice sheet had a lot of marine based parts, and the British and Irish ice sheet as well is very much influenced by the ocean. So those can eventually tell us some information about the response to the ocean. But at the moment, I think we need some better information on how we can parameterize subshelf melt to be applying those models. But I know colleagues are doing it around the world, and we are planning to do it to start doing this very soon.
Do you think the British ice sheet is a good one to look at for ocean constraints? Because you probably have a lot more data around there to constrain the Paleo Ocean than you do elsewhere.
Yes, it potentially is. It is also, so the British ice sheet is also quite influenced by the surface mass balance, balance of both. And there's a lot of accumulation. So our ability to represent accumulation of snow on the ice sheet is also quite important. So we need to strike a balance between our ability to quantify uncertainties from the ocean side and the atmosphere side. But I think it is definitely promising, and we have shown that its retreat was influenced by marine ice sheet instability. So it's got the potential really to challenge our models and test them in context different from the future. It's also smaller, so it's easier to simulate from the ice sheet side of things. But from the climate side of things, we do need regional climate models for this ice sheet.
Next up, we have a question in the chat from Letty. I think Letty has the flu at the moment, so she's asked me to read it out. Do the albedo parameters you need fall within reasonable bounds, or do they change much from their default values?
Yeah, I think they were on quite extreme side, and now they fall within much reasonable values. Some are not directly applicable to the real world. Sometimes it's things like that you wouldn't be able to measure in the real world because of the low resolution of the climate models. So things like the relationship between density of the snow and its albedo, for example, or we have some parameters that control the albedo in the ablation areas, for example, trying to represent how melt ponds might darken the surface in the summer. And it's very difficult to relate those as, they will be dependent on the resolution of the climate models, but they are definitely much more reasonable now.
So with those ones that are dependent upon the resolutions, it's not entirely clear that if they're realistic.
Yes, that's right. It is more difficult to just put some bounds on them, but we can look at the effects on the albedo at the surface of the ice sheet, and how that varies through in sort of the interior of the ice sheet and in the ablation zones, and so definitely our results are more reasonable.
Next up, we have Brian and then Jeremy. Brian, is there any chance you'd like to unmute?
Yeah, sure. I was just curious as to whether the dust was interactive with the clouds, whether the dust was going to serve as a ice nuclei or not.
So it's not in famous, but there are some more complex models where that's possible. I don't know if any have been applied to the Last Glacial maximum where we've looked at that actually. Yeah.
Barely been applied to the present, so.
Jeremy, would you like to unmute?
Yeah, I had a quick question. One of the things that we always struggled with the Laurentide was we could barely convince the ice sheet to advance into the Hudson Bay. And if we could manage to get it to advance in the Hudson Bay, we couldn't get it to leave the Hudson Bay. And so I guess that's my question is, once we got it to advance, it was extraordinarily stable and we could not simulate deglaciation. So is it possible that processes at the margin and processes associated with the Hudson Bay? Yeah, we had isostatic adjustment in, Gavin. It really didn't like to advance into the deepest water of the Hudson Bay. And is that possibly related to the fact that you had a hard time getting a stable ice sheet?
So we anticipated that problem and actually started with ice over those deep parts to avoid a problem of growing the ice sheet. There's also some limitations in the coupling between the climate and the ice sheet. That means that we can't initiate an ice sheet from nothing. We have to start from something. You know, that inception of the ice sheet is a difficult thing to represent, I think, in climate models. So we started with ice there. But some other work that we've done with BISICLES to simulate the 8.2 kilo event, for example, we have managed to retreat the ice sheets in Hudson Strait. So I'm just wondering whether there's anything that would have helped. I don't know. It is possible that it's just the way BISICLES represents the grounding line helps retreat in Hudson Strait. Maybe that's something that we will be able to look at next.
Thank you.
Thank you, Jeremy. Do we have any further questions, perhaps final questions from anyone? Very quiet for a moment.
Okay. One more question. So, what's the climate sensitivity of famous?
Oh, that's a good question. So we should probably. So we've got an ongoing project with our colleagues in Reading that is really applying famous ice in LGM present and future, and we're varying parameters that changed probably the climate sensitivity. So that's something that we should probably verify. And I can get back to you on how the quantification of uncertainty that we're doing affects the climate sensitivity. It's also different. The reason I don't want to answer is because the version of famous, coupling famous with the ice sheet has changed it from previous versions we've had before. That would again change the climate sensitivity. It's not something that we've calculated recently.
Yeah, but if you need more ice, right? I mean, you could just increase the climate sensitivity so that you got colder, right? I mean,
yeah, and I mean, at the moment, what we're doing is through changing the sea surface temperatures. You know, that's a way, or the sea ice concentrations. That's a way to cool things down, or the cloud parameters. That will
is famous in energy balance.
It's a full GCM, yeah.
Well, no. But if you're
in energy balance, so yeah.
If you're setting the SSTs, then it's doing its own thing in the atmosphere, but it can't get rid of an imbalance. Yeah. And so, is the top of the atmosphere energy flux close to zero or not? That might be a clue to what in the overall climate scheme of things is going on.
Yeah, and again, that's not something that we check in those simulations. Now we've moved on. What I haven't mentioned is that we've moved on to using slab ocean and dynamical ocean for the Last Glacial Maximu and the deglaciation, and also we're now simulating the penultimate deglaciation like this. So that changes as well the behavior of the model, and we're planning to look in our ensembles at the top of the atmosphere fluxes to check that.
Yeah, I mean I think that might be quite useful, and then you could kind of pin down. Well, not me, but anyway, it might give you some clues about things to adjust in order to maintain stability.
Yeah, that's right. And you know, the way we run our ensembles really depending on what we want to do with them. Sometimes we just want to have a range of model behaviors. Sometimes we want to have a range of ice sheets that are physically plausible, but that might mean that the rest of the climate isn't necessarily well simulated.
Well, physically plausible, like you can't have a massive energy imbalance at the top of the atmosphere, right? That's a very clear plausibility check.
Yeah, if you consider the climate system as a whole. Yeah.
Right. But are we not?
Well, it depends on what you want to do. And sometimes it's useful to generate ice sheets to have a look at, their effects on sea level. And we know that we can't get the full system plausible, but maybe a subset of the system might give us some interesting clues. Or for example, if we're interested in the ice streams,
right?
You'd still need a reasonable surface mass balance, but maybe the full climate system doesn't necessarily need to be in balance. But yeah, that's the kind of discussions we have at the moment, is to, you can use the ensemble to sort of have a subset of simulations for different things you want to answer, different questions you want to answer.
I would be particularly interested in the subset of simulations that are energetically balanced.
Yeah. Okay.
Right?
we'll work on that.
And so, and hopefully, of all the simulations that you have, some of them are, but will have like kind of slightly different ways of getting there. And that I think is useful, because you want to have those external constraints so that you can winnow out the big large spread, right? Because that they're not all equally valid, right? And when they did, this goes back a while, when we did when they did the climateprediction.net kind of ensemble spreads, a vast majority of those were not energetically balanced, and in fact, most of the variation and the extreme variation that they published was related to models that were not plausible in the end. And so kind of like this kind of helps you kind of, I think, narrow down into places that are plausible climatically, and that makes your life, I think, a little easier, because you have not 1,000 different things, but maybe 5, right? And then you can really ask yourself why those 5 are not any of the others.
Yeah, that's really useful, actually. Yeah, I think we'll work on looking at the energy balance in the climate as a whole. Thank you, Kevin.
Thanks, Kevin. Do we have any further questions? Silent. So I think we should probably close off soon. Thank you again. Thank you again ever so much for speaking to us today. It's been really fascinating. I look forward to uploading this to YouTube. Thanks everyone for joining us.
Yeah, thanks a lot, Lauren. Like I said, it's great to see you, and you guys are doing great stuff. So
thanks, Kevin.
Let's keep in touch.
Thanks for the invitation. Thanks for coming and all the questions and the feedback.
Cheers, everyone. Have a good day.